Hello everyone. Thank you for joining our webinar today, Permanganate 101. I am Liz Mueller, Direct Marketing Specialist with Carus Corporation, and we will have Mr. John Bull presenting today. A few housekeeping items. We do have everyone on mute to help keep the background noise down. There is a feature within GoToWebinar where you can type in your questions. Please feel free to type in your questions as you think of them. We should have time at the end for a question and answer session. If we do not get to a specific question at the end, we can see the specific email address that asked that question and we will follow up with you directly. Also, we will share a PDF version of this webinar to all the attendees. So I will email that out either this afternoon or tomorrow. Here's just a quick look at our remaining 2016 webinar series. So on April 11th, we will have permanganate for oil and gas applications. May 9th and December 12th, we will have lead and copper control with phosphates. And then we will repeat this webinar on November 14th. So if you are interested in joining any of these webinars, please let me know. I will get you registered. Also, we send out periodic newsletters and email blasts. If you are currently not on our list to receive these but would like to be added, please let me know. With that, I would like to introduce Mr. John Bull. He is currently the Technical Service Manager for Carus Permanganate Business Group. John has been with Carus Corporation for over 40 years, serving in the variety of sales and marketing positions. The Technical Service Department provides chemistry and applications customer support, including on-site lab testing and plant-scale startup and troubleshooting services. John earned his BA in Engineering from Purdue University, West Lafayette, Indiana. He is a member of the Water Environment Federation, WEF, and the American Water Works Association, AWWA, where he has served as the AWWA Illinois Section Chair from 1992 to 1993.
All right, thanks, Liz. And welcome to all of you who are attending today's webinar. Thanks for participating. I'm John, and I'll be your presenter for Permanganate 101, which is our overview of permanganate chemistries and applications. In the next 45 minutes or so, I'll take you through a variety of topics, starting with a brief introduction to Carus Corporation and our permanganate products. Then I'll review, in a user-friendly way, I promise, oxidation chemistry. And finally, I'll finish with permanganate-specific chemistry and its applications. So first, let me do an introduction to Carus Corporation. Carus has been the leader in permanganate products and applications research for over 100 years now. We're located in Northern Illinois, and also operate offices in Europe, and we sell permanganate products globally. Carus is the largest permanganate production facility and the only permanganate manufacturer in the Western Hemisphere. Our chemistry expertise is in permanganate, manganese, and oxidation chemistries, and our marketing focus is in the areas of drinking water treatment, wastewater contaminant control, industrial oxidation processes, and environmental pollutant remediation. Now, I would hope that many of you are already familiar with our line of products, but for those of you who are not, I'll describe them for you briefly. Permanganate is available really in two basic formats. It comes as a dry crystalline material, which is traditionally how permanganate is manufactured, and it comes now as a concentrated liquid product. The dry products are subcategorized into different grades, and these grades vary slightly in their purity or their assay. Although permanganate is rarely less than 95% pure. They may also be blended with additives to improve their performance, as in the case of free-flowing grade permanganate, which is designed for use in high humidity areas. Dry permanganates may also be segregated by their particle size so that different grades may reflect different sieve fractions. The liquid products are aqueous solutions manufactured either as 20% or 40% concentrations. So permanganate, in its dry form, is potassium permanganate, chemical formula KMnO4, and in its concentrated liquid form as sodium permanganate, formula NaMnO4. And you can see that in both cases, the permanganate ion, MnO4, is the same, and the chemistry between these two products is also the same. Permanganate is a stable compound under normal conditions, so it can be manufactured at one location, packaged, and delivered to the user site where they can use it when needed. The manufacturing process starts with manganese dioxide ore, which is plentiful in the Earth's crust and is a mined product. We simply take that ore and we apply oxygen, heat, and energy to raise the manganese oxidation potential from +4 in manganese dioxide to +7 in permanganate. Now, when the customer uses permanganate, they're simply reversing the process and taking the energy out of the permanganate for whatever important purification step they might be doing, and then they are left with manganese dioxide solids at the end. Now a bit about oxidation and reduction chemistry. So permanganate is the proud member of a special chemical designation, oxidizing agents. It shares this important group with other commercial products such as chlorine, peroxide, chlorine dioxide, and ozone. And for those of you who may not be familiar with oxidants or oxidation chemistry, it may be helpful just to think of oxidizing agents as a form of energized oxygen. It's likely that the name oxidation is a result of observations of our physical world. We live in, after all, an atmosphere of oxygen. And it was soon noted that almost all elements form oxides or oxide compounds by just being exposed to the air. In the first example above, you can see the reaction for iron reacting with oxygen to form rust, which is a relatively slow oxidation process, but one that goes on constantly around us. When heat and light are involved in a rapid oxidation reaction, it's often referred to as combustion. So you can see in the lower reaction, we have an organic material, in this case a sugar, that is reacting rapidly with oxygen and will actually burn to form carbon dioxide and water as the oxidation products. Now, to a chemist, the definition of oxidation reaction is really a little bit more complex and maybe more accurate to consider it as a transfer of electrons from one element to another. This means that oxidation reactions are always paired with some type of reduction reaction. You really can't have one without the other. The oxidizing agent or oxidant is responsible for oxidizing another substance, and itself is being reduced. And in this case, oxidation means the loss of electrons, and reduction means the gaining of electrons. Permanganate is a manganese compound, and manganese is found in the top central portion of the periodic table, symbol Mn, and it has an atomic number 25. It's located right next to iron in the periodic table. And as with iron, it's common in the Earth's crust. Manganese is an essential nutrient for life, and it has several large-scale commercial uses, including in the manufacturing of steel. It is often found as the cathodic material in rechargeable batteries. And of course, it's used to manufacture and make other types of chemicals. Manganese falls into the category of a transition metal. And transition metals such as manganese lend themselves nicely to oxidation chemistry because they have many electrons that they can share with other products. Manganese in this case has 11 electron positions available in its outer shell, which can pass back and forth during oxidation reduction reactions. So let's look at an example of a very common reaction for permanganate, the oxidation and subsequent precipitation of dissolved manganese plus 2. You can see that there are two reactions paired together. In one, permanganate, the MnO4 ion, is reduced from a +7 oxidation state to a +4 state as manganese dioxide MnO2. The dissolved manganese plus 2 is oxidized in this particular case and also results as manganese dioxide plus 4. This is a rather unique reaction known globally in the water treatment industry, and it provides many very practical functions. Here's another example of an oxidation reaction involving organic material. And in this case, this example shows what it might look like when you do not have complete oxidation to carbon dioxide and water. In environmental applications, the reactions are generally incomplete, simply fragmenting large organic molecules into smaller ones. But this can be very practical and very important. Now, all oxidants, and permanganate is included, can do some reactions very, very well. In the case of permanganate, when the organic material has some type of unsaturation associated with it, where it has double or triple bonds, permanganate is extremely effective at breaking the organic molecule apart at that particular functional group. There are also other functional groups that permanganate will react with quite readily. And those include alcohols, aldehydes and ketones, and the analogous products that are sulfur or nitrogen-based, such as amines and mercaptans. Now, the interesting thing about these types of reactions is that functional groups, along with the structure of the molecule, are often what provide the characteristic taste, odor, or color associated with that material. So if you can oxidize and destroy the functional group, you can often make that product less odorless, tasteless, or colorless, which is exactly what we try to accomplish in many permanganate applications. And here's an example just to show that permanganate reactions can be pH influenced. Now, in most environmental reactions, we're working within that center range of pH 3 on the low side to pH 12 on the high side. In those pH ranges, permanganate will react in a 3-electron transfer to produce manganese dioxide solids as the byproduct of the reaction. In special cases, you can force the pH to the extreme ends, either very acidic or very alkaline. And in that case, the reaction mechanism changes just slightly. Under very acidic conditions, permanganate can accept 5 electrons in a transfer, going all the way to dissolved manganese plus 2. And in an alkaline condition, permanganate can lose or accept 1 electron and convert from permanganate to a product called manganate. So why is oxidation chemistry important? Well, it's important because it's very versatile technique. It's a very versatile technique. So in very simple terms, oxidation chemistry can be used to make or synthesize other types of organic materials. And this is what you normally see when you go to a textbook, a chemistry textbook, and look up permanganate oxidation reactions, because chemists spend a great deal of effort to try and determine pathways for manufacturing different types of organic materials. The flip side of that is that oxidizing agents can also be used to break down large organic materials into smaller ones, which are either less toxic or less odorless or tasteless compared to the original material. On a commercial basis, oxidizing agents are used for a variety of different applications and can generally be categorized in one of four major buckets. The synthesis or purification reactions that I was just talking about are one area of high oxidant use. To one degree or another, oxidants are capable of removing color from different products, so they are great for bleaching, as you might expect. When you think about chlorine or chlorine bleach, it's exactly what we're doing, is decolorizing, for instance, textile material or pulp and paper, for instance. And permanganate does have some application areas there. Oxidizing agents are also disinfectants and therefore can be used for therapeutic uses. Permanganate is not itself registered as a biocide, but will have biocidal capabilities, and there's a great deal of literature that addresses that. And then finally, where we spend an awful lot of our time and effort in supporting our customers' work is in the bucket of environmental chemistry. So let's move on to specific permanganate chemistries and the applications that they are used for. So then that synthesis bucket, permanganate has had a long history of use for producing other materials. And probably the one known best for permanganate is the production of saccharin as an artificial sweetener. There are many small permanganate manufacturing plants dotted globally around the world that were actually captive use plants for a saccharin manufacturing facility that was located right next door to the permanganate plant. This was a great application until probably the early 70s, when saccharin was identified as a potential carcinogen, and it lost its market as an artificial sweetener. There are therefore a lot of permanganate plants that were available at the time for now selling permanganate on the merchant market. So in addition to the production of saccharin, permanganate has been used to manufacture antibiotics. It's used in the ag business for manufacturing a variety of active ingredients that go into herbicides. And permanganate has also been used to manufacture different types of vitamins such as ascorbic acid. And here's a brief list of some of those particular applications, which are very unique and lend themselves nicely to oxidation chemistry. Oxidants such as permanganate can be used to purify other chemicals. For example, permanganate is used to improve and purify food-grade carbon dioxide, especially when that carbon dioxide source is providing some type of sulfur contamination that needs to be removed before that CO2 can be used in beverages. Permanganate is also used to purify and clean nitrous oxide, which is used as an anesthetic. And it's also used by the zinc industry to purify zinc in the zinc manufacturing process. I mentioned that permanganate has some applications in bleaching, and probably the most common one currently is the removal and destruction of the blue aniline dye in denim. And permanganate is used to pattern or produce a particular fashion look with denim blue jeans by bleaching out the blue color in various patterns. Permanganate is also used to bleach beeswax to produce a very white product that can be used for manufacturing candles or for coating pills. Permanganate has also been used to bleach kale and clay, and of course is used to remove color from drinking water supplies. I mentioned that all oxidants to one degree or another are disinfectants, and there are many, many applications that have been written and studied where permanganate has been used to control pathogenic bacteria or viruses, or even fungus, where permanganate was used to control athlete's foot. And an offshoot of these particular applications are applications that are medicinal or therapeutic. None that are probably currently being used, but certainly are of unique interest. For instance, there is literature written that permanganate can destroy snake venom and has been used to treat wounds as a result of snake bites. Permanganate is also used to soothe the rash created from poison ivy, because it will oxidize and destroy the oil that is creating the irritation. In an actual commercial application, permanganate is used by the aquaculture industry when raising fish in a farm or in a pond or raceway. In these particular types of applications, the animals are intensively grown, meaning that they are growing in very dense populations. And in those situations, it's very common for the animals to suffer from different types of diseases. And permanganate is used by the catfish farming industry to control external parasites on the skin of the fish. And it's also used in the farm raising of trout for the same particular type of application. Permanganate, of course, can also be used just to purify the water that the animals are being grown in. Now, in a slightly different niche industrial market, we know that permanganate is used for the cleaning and surface preparation of different types of carbon steel metals. And in particular, when the metal product is going to be coated or plated in some way, it's necessary to have a very smooth and clean surface so that coating or plating will stick nicely to the product. And we find that permanganate was useful for cleaning metal rod or metal wire or other types of metal products such as screws and bolts or other decorative types of forms. In this particular case, the process used is a very alkaline permanganate solution at high temperature. It's a batch operation where the metal part is immersed in a bath of permanganate. And then the permanganate pre-treatment is always followed by traditional acid pickling to remove the final amount of scale and the manganese oxide from the surface of the metal. Now, it's interesting to note that this chemistry, while it worked quite well for the metal industry, also works well in the plastics industry as well. And the current commercial end use for that is in the preparation of printed circuit boards when it's necessary to plate the copper connections between the components and also between different layers of the printed circuit board when a multi-layer circuit board is being prepared. In this particular case, it is very critical that the copper plating sticks well so that the electrical connection is not lost. And it's more difficult actually to have copper plated on smooth plastic than it is actually on metal, which can tend to be rough in its surface. So permanganate is used for two reasons. One is to clean out the holes or vias that are drilled into a board when you need to communicate from one layer to the next. And it's also used to slightly etch the surface of the plastic material so that that copper plate will stick much more tenaciously and stay in place. There are also metal surface treatment applications where permanganate is used to clean different types of equipment. One example is in the maintenance and inspection of the hot sections of jet engines, where a heat scale can form during operation, and it's necessary to remove that heat scale during the maintenance operation so that the parts can be inspected for cracks or weaknesses. Permanganate applications are also found in the nuclear power industry when, in this case, radioactive heat scale needs to be removed from the inside parts of different reactor pieces of equipment. And also it is used in the refinery industry to clean pyrophoric iron sulfide scale off the inside of different parts of the refining process. Permanganate also has small applications in cleaning organic scale off of equipment such as heat exchangers or dyes when fiber material is being prepared. Now, there are a great many applications for permanganate in what I would call the environmental end use applications. And I'm going to talk about some of those right now. The first is the oxidation and destruction of unwanted cleaning solvents that were used by the metal industry or by the dry cleaning industry and may have leaked or been discarded into the soil. Permanganate is very effective at oxidizing and destroying perchloroethylene and trichloroethylene, which are common cleaning solvents. And in this particular application, permanganate is injected directly into the contaminated soil, where it destroys the material without having to remove the soil and replace it in an in situ type of treatment process. For really over 50 years now, permanganate has been studied and promoted for use in the purification of drinking water. And it is used either by surface water treatment supplies or groundwater treatment supplies. And in these particular cases, the oxidation reactions may be necessary to remove natural or man-made inorganic compounds, which are typically iron, manganese, or sulfide materials, or that can be used to remove natural or man-made organic materials, such as taste and odor compounds, disinfection byproduct precursor materials. That is organic materials that will react with chlorine, which is our disinfectant in the United States. It will remove organic color and just reduce the organic loading of the water in general. And probably the current hottest topic right now in the water industry is the need to destroy and remove toxins that are produced by algae blooms in the surface water treatment supplies. And then finally, as I mentioned, all oxidants to one degree or another will remove biological contamination. And at this point, permanganate is not registered for a biocide use, but can be effective for destroying bacteria when permanganate is being used for other water treatment applications. In a surface water treatment plant, which is a conventional settling and filtration design, permanganate is often the very first chemical that is applied to the water. It is applied early in the process really for three reasons. One, we need some reaction time to allow permanganate to complete the reactions that we wanted to get to. Secondly, permanganate, when you add it into the water, is pink or purple in color, so we want that color and the permanganate to go away by the time we get to the flocculation and settling area of the treatment process. Because then the byproduct of the permanganate oxidation reaction is the particle manganese dioxide, which needs to be collected and removed in that sedimentation and filtration process. And then finally, if permanganate goes first into the water supply, we can minimize interaction with other treatment chemicals, such as powdered activated carbon. In groundwater supplies, the application is much simpler. It generally involves only a single pressure filter system where permanganate is injected into the water just upstream of that filter. And the permanganate reactions, which are typically iron and manganese, can proceed rapidly in the raw water pipe going to the filter and in the headspace at the top of the filter. What helps permanganate in these particular applications is when the water is particularly hard, which is not uncommon for groundwater supplies, and when there's a minimum of organic content. Now, not only is permanganate used on the drinking water side of municipal water treatment, but it is used on the wastewater side as well. And typically the applications have to do with odor control. In wastewater treatment, biological activity, especially when dissolved oxygen is no longer present and the system has gone septic, odors are produced. And these odors are generally released whenever we're doing any type of physical activity with the water itself. So anytime there's high temperature or high surface area and we're pumping, mixing, spinning, or squeezing the water, we will drive odors out of that water and into the air. And if that's the case, then if we can treat the wastewater just prior to those turbulent areas, we can destroy the odor compounds before they're released. So why is permanganate used in general by the wastewater industry? First of all, it's used to protect the operators, because in wastewater, the single largest odorous compound that's produced is hydrogen sulfide. And hydrogen sulfide, even in relatively low concentrations in air, can be irritating when you're exposed to it, and in very high concentrations can actually be toxic. So removing hydrogen sulfide protects the workers in particular wastewater treatment areas. Hydrogen sulfide will also react with moisture in the air and with bacterial action to produce sulfuric acid, and the sulfuric acid can be very corrosive to concrete and metal parts and equipment in the wastewater treatment plant. Of course, hydrogen sulfide can be detected by the human nose at very low concentrations as a rather obnoxious odor, and to improve the goodwill with the neighbors in the area of a wastewater treatment plant, odor control is always an important step along the way. Sulfide will also tend to interfere with the biological processes within the treatment plant, so by removing sulfides you can improve the process efficiencies. And the one thing you do get with permanganate when you're talking about odor control is you get very rapid oxidation reactions to take place. And there are really two strategies for applying permanganate to wastewater treatment. One is by applying it directly into the wastewater and destroying the odorous compounds before they're released. And the other is to collect odorous air and pass it through some type of cleaning device, such as a wet scrubber or a dry scrubbing system. In the case of gas scrubbing, permanganate is made either as an aqueous solution of 1 or 2% concentration and recirculated through a tower containing packing, and then the gas can be passed through that and washed by the permanganate solution. There are also products available on the market where permanganate is coated to the outside of a solid media of some type, typically spheres, which may be aluminum or aluminate in structure. And then a bed of dry pellets is put into place and air can be passed through it to remove low-level concentrations of odorous materials. So in wastewater treatment, permanganate is applied in different areas of the process, including in the collection system where wastewater is picked up in the residential area and directed toward the wastewater treatment process. The collection system often involves gravity mains as well as force mains where a pump station collects the wastewater and then pumps it into a pipe under pressure. All of these cases, wastewater can be out in the collection system for a long period of time, sometimes days, and the biological activity will soon consume all of the oxygen in the wastewater and the material will go anaerobic and bacterial action will then produce a lot of different types of odors, including hydrogen sulfide. So applying permanganate in a collection system can remove those spots where odors are being released. And then eventually the wastewater arrives at the treatment works. And if it is septic when it arrives, then there can be odors at the headworks of the plant, where it may be necessary to apply permanganate as an oxidizing agent to destroy odors that are released at that point. And also other early processing steps, such as grit chambers and primary clarifiers, are common application areas for permanganate. Now, permanganate is even used in the secondary treatment process, although that system is being aerated and has a very high dissolved oxygen level. But it is very turbulent because of the application of the air or oxygen at that point. And so if any odors enter into that system, the process will strip them out of the water and into the air, creating a neighborhood odor complaint. And probably the most common area and popular area for permanganate use in wastewater treatment is when biosolids are being dewatered. Again, the mechanical dewatering system will tend to squeeze the water out of the solids and release odors into the room or into the atmosphere. And by treating the biosolids with permanganate prior to this process, we can destroy the hydrogen sulfide or mercaptan odors. We can improve the performance of the polymers that are being used to dewater the solids. And we can eliminate the return of odorous materials from the dewatering area back to the headworks of the treatment process. And don't forget that not only are odors generated in municipal wastewater treatment, they can be common and found in industrial wastewater treatment as well. So industrial wastewater treatment with permanganate often involves odor control. And it can be in very simple types of wastewater treatment processes. So in ponds or lagoons where wastewater is being collected and treated, permanganate can be used to destroy the odors that come off of those areas. And for instance, in the municipality, there may be landfills close by where solid waste is being disposed of, and those landfills will collect leachate that comes off because of rainwater, and that can be very odorous when it's pumped back into the sanitary sewer system. There are applications for permanganate in the mining industry, and typically at this point they're for mine drainage or wastewater treatment to remove iron and manganese, very similar to what's happening in drinking water purification. The only difference in these applications is that their pH range on the wastewater is very, very low. It's very acidic, and it's also necessary to raise the pH of the system along with the oxidation reactions with the permanganate. And odors are also generated not only by human activity, but by animal activity as well. So permanganate can be used in the agriculture industry to control odors at cattle feedlots or any type of concentrated animal feed operation where animal manure may be collected and removed. There are new regulations and a lot of scrutiny of this particular industry, so it's not uncommon to see odor requirements necessary for animal feed operations and animal raising types of operations. A little bit more about industrial use of permanganate in refinery applications. I had already mentioned that permanganate is used to remove pyrophoric iron scale off the inside of refinery equipment. That's because the pyrophoric scale, which forms under an inert atmosphere or an oxygen-free atmosphere, is very reactive when it is exposed to oxygen in the atmosphere and can in fact get hot and create a fire. So the removal of pyrophoric iron before equipment can be opened for maintenance work is very, very important, and one where permanganate is extremely fast and easy to use. In refineries is one of those application areas where phenols as a specific type of organic contaminant may be present in wastewater treatment. And phenols are regulated so that they are not discharged into the environment in general. And phenols are oxidized very rapidly by permanganate and destroyed easily. You have hydrogen sulfide and other organic sulfur compounds such as mercaptans that are destroyed by permanganate in order to get odor control. Permanganate can be used for the oxidation and destruction of cyanide. And also the manganese dioxide that forms during the permanganate oxidation reaction can be used as an absorbent for positively charged metal ions. And the industry has found that the use of permanganate in wastewater can also help to remove compounds such as selenium. The phenol application areas are not just in refineries. There are many types of industries that use or produce phenol in their processes. And all of these are sites that can use permanganate to destroy phenol contamination. Centralized waste treaters, where industrial wastewater is collected and taken to a central point for processing, are a good example of where phenol destruction with permanganate is used. Permanganate is used for phenol because it can consistently remove greater than 99% of the phenol present in the wastewater. It does not require any particular specific pH range for performance. We can treat generally at the pH of the wastewater as it arrives. Permanganate will destroy phenols in 30 to 60 minutes, and it can be very cost effective to use permanganate in this way. And then finally, just to wrap up, you've seen in a number of these slides pictures of permanganate in solution, and you can recognize the characteristic pink or purple color. This is just another example to show you that the permanganate color is actually related to the concentration of permanganate in solution. And as the concentration goes up, the color gets darker. And we can use that to our advantage to monitor for permanganate residuals in water and actually determine how much permanganate is present in any particular time in a process. Permanganate can be seen visually with the eye down to concentrations as low as about 0.2 or 0.25 parts per million. And at levels below that, you can use a laboratory spectrophotometer to measure permanganate color directly as well. And we use a lot of HOC-DR type of field test equipment for monitoring permanganate concentrations in field applications. So then to summarize and just conclude the webinar, I would say that permanganate is an oxidizing agent that is very versatile and can be used for a variety of different applications. The applications fall into municipal areas of water and wastewater treatment, industrial niche applications such as synthesis, and of course also in industrial wastewater treatment. And then finally in environmental applications such as odor control, gas scrubbing, and in situ chemical remediation of unwanted solvents that may be contaminating soils. And with that, we'll end the webinar and ask for any questions that you might have. So one of our first questions is about treating of drinking water supplies for taste and odor control. And the question is, how does permanganate compare to taste and odor control with pre-ozone? Well, I would say that probably the gold standard for any type of oxidation reaction in drinking water treatment, ozone is probably it. The oxidation reactions with ozone are rapid and effective. The only real difference is that ozonation generally does not carry a residual very far into the process. And so it can be limited in how it's used, and there may be some cautions associated with it as well. So for example, they are looking very closely, and the EPA is always concerned about what the byproducts are from oxidation reactions. And there are some byproducts that ozone can form when it's applied to raw water supplies that may not be advantageous to produce. Ozone is often very effective as well in settled water supplies where it's not being applied to such a high concentration of raw water organic material. And it finds very effective use there. And an example of why you might be concerned about that is this topic of algal toxins, where ozone is such a strong oxidizing agent that it can rapidly lyse and open algae cells, which is not necessarily a good thing that you want to do, because then the toxins that are within the cell are released into the water supply. And because the ozone residual is only short-lived, there may not be enough oxidant there to destroy all of those toxins when they are released from the cell lysage. So there are positives and negatives compared to when comparing permanganate and ozone together. So there's a question also in that same category about geosmin and probably MIB, which are the two compounds of most concern from a point of view of taste and odor control in the drinking water industry. And those compounds are not oxidized by permanganate, so it's generally very common that permanganate is used to remove other organic materials besides the MIB and geosmin, and then carbon follows the permanganate addition to absorb and remove the MIB and geosmin that's remaining. There is indication that says that ozone can and will remove MIB and geosmin, and pre-oxidation with ozone also does very well at breaking large organic molecules into smaller ones so that the organics can be used as food by biologically active filtration processes later on. There's a question about wastewater sludge odor control and what the typical application rate is for permanganate. Amazingly, regardless of where we go across the country and test wastewater sludges, the application dosage always seems to fall within the range of about 50 parts per million to 100 parts per million as permanganate into the wet solids that are going to the dewatering device. Another good way of, or another rule of thumb that you can use in that particular area is about 1 pound per 1,000 gallons of sludge to be treated. It's a good starting dose, and then you can evaluate from there by measuring the sulfide concentrations above the dewatering device to determine whether you need to go higher or lower. One of the aspects of biosolids that will affect the permanganate dosage requirement is how concentrated those solids are. So if the solids are coming in at, say, only 3 or 4% concentration, the permanganate dosage will be lower. If they're coming in at 5 or 6% concentration, the permanganate dosage will be slightly higher, and that's just because of the organic content of the waste when the permanganate is being injected in. There's a question about any experience with glycol oxidation. Ethylene glycol can be oxidized by permanganate. It probably is pH dependent, so the higher the pH in this particular reaction, the better it will be. And in oxidation reactions, there's always an aspect of concentration that's involved in the reaction. So the more concentrated the contaminant is, the more likely you are to get a fast oxidation reaction to go. So at very low concentrations, part per million levels, it may be difficult in, for instance, cold water to get that ethylene glycol oxidation reaction to go at any speed that is practical. It really needs to be tried at an individual site to determine whether or not the glycol can be removed at a high enough ratio to make it practical. So there's a question about whether or not an e-file of this presentation can be received for your records, and the answer is yes. A PDF will be sent to everyone who's participating in the presentation today. And then there's a question about how effective is permanganate for removing and reacting with TCE and PCE. Well, that's the primary application for in situ chemical oxidation in soils, where the concentrations of the TCE and PCE are very, very high. Now, the reaction mechanism changes when you're talking about low levels of TCE or PCE in water. So when they're in the parts per million range, the reactions begin to slow down quite significantly. And you may not have enough time in, say, a drinking water treatment process to remove those particular types of compounds. In that case, pH may be an important factor. And I think that may be it. Are there any other questions that anyone may have at this point? If not, we thank you for participating today, and if any questions do arise later, please let us know and send us an email. Thank you.